Hello Year 9 and welcome to this lesson from our electrical circuits topic on resistors. And so we're going to look in a bit more detail. This is the second lesson and we're looking at the rules of resistors in both series and parallel circuits. So let's start. You should have completed the starter activity with your teacher already. So let's just start with a little bit of a recall of what we mean by resistance. Okay, so we should remember that resistance of an electrical component is just a measure of how difficult it is for the electrons to pass through the atoms that are vibrating in a metal component. So if we think about, for example, the metal filament in a bulb, okay, as we start to pass electrical charge through that, that excites the atoms in there. They start to vibrate a bit more. Therefore, the electrons that are trying to pass through find that more difficult, and the resistance builds up, and the if filament heats up and starts to glow and makes our bulb light. Okay, now if we remember, we define resistance as being the amount of potential difference across a component divided by the amount of current that is flowing through that component. Okay, and if you remember, at a constant temperature, that is directly proportional. We measure it in ohms with that funny squiggly symbol. Okay, and as I say, for a given potential difference, so at any potential difference, if we maintain a potential difference across that component, the more resistance there is, the smaller the current. So as we increase resistance, we decrease current. Okay. So let's look first of all at resistance in series circuits. So here's a very straightforward series circuit. Okay, you can see we've got a 1.5 volt battery here. Okay, we've got a lamp and we've got a variable resistor in series, and then we've got two voltmeters. Voltmeter 1 across the lamp. So I'm going to write in here that this refers to my lamp, and I've got voltmeter 2 across my variable resistor. Okay, so we're going to look at some data and look at how resistance changes and how resistance is in this example. Okay, now notice that under normal conditions with the bulb lit, okay, the voltage across the bulb is 1.5 volts. In fact, it's the same as the battery. Okay, and in this instance, there is no voltage across the variable resistor. So our total voltage, our total potential difference in the circuit is 1.5 volts, and all of that is across the lamp. Now, as we increase the resistance in the lamp, okay, what happens is we start to get a decrease in potential difference across the lamp and an increase in potential difference across the variable resistor. But notice that those two numbers still add up to 1.5 volts. Okay, as in the bottom one as well, where it gets when the bulb is now very dim. Okay, the voltage across the lamp is now 0.5 and across the variable resistor is 1, but it still adds up to 1.5 volts. So let's look in a bit more detail at some numbers here. So we're going to take this one here as our example. Okay, let's suppose that the current around our circuit is 0.1 amps. That's our current, I. Okay, 0.1 amps. Now, when it's dim, we can work out what the resistance would be. So if we recall our equation that links all of these things together, V equals IR. Okay. Now, to work out resistance, we therefore need to take our voltage and divide it by our current. Okay. So in this case, for the dim bulb, for the dim setting, we're going to have a voltage here through the lamp of 0.9. Let's just write R equals. And our current, as I've just said, is 0.1. So therefore our resistance is going to equal 9 ohms. Okay, that was the funny squiggly symbol, 9 ohms. Now, what's the resistance of our variable resistor at that point? We use the same equation, but this time we've got 0.6 divided by the same current, because we know that the current in a series circuit is the same anywhere. So that gives us a resistance there of 6 ohms. Okay? So what we can see is that the total resistance there is going to be something of these combined. Okay, now if we replace these two components, if we took the bulb and the variable resistor out and replace them with a single resistor, okay, in order to maintain that same current with that potential difference, that resistor would need to have a resistance of 15 ohms. Okay, so a single resistor would have to have a resistance of 15 ohms for the current to still be 0.1. And we can show that, okay, because if we want to work out current, we can show that our voltage is 1.5, our resistance is 15, okay, that would give us a current of 0.1. Okay, so therefore what we've proved here is that the resistance in a series circuit is the sum of the resistances of all the components, in this case the two components, but any number of components, the sum, and that same rule applies to any series circuit. And I'd like you to write this down as our first rule. Okay, so the total resistance of two or more components, the total resistance is equal to the sum of the resistance of each component. So in my example here, I can show that, okay, by showing you, if I don't know, I can even just work this out, what the total resistance is without knowing potential difference or current, because what I can say is that my total resistance in this circuit here is going to equal R1 plus R2 plus R3. So my RT is going to equal, let's write these numbers, 10 plus 20 plus 10, 40 ohms. Okay. So what we know therefore is that when we add more resistors in series, this increases the total resistance of the circuit because the potential difference is now shared between more resistors. Okay, so we know that the potential difference doesn't change. Okay, as a result, there's less potential difference across each of them. Okay, the current through the resistors is therefore less because there are and because the potential difference is unchanged, the total resistance is therefore greater. Okay, so let's look at parallel circuits now. Okay, so here's a typical parallel circuit. We've got a variable resistor, a battery, an ammeter here, and 2 ammeters here on our parallel part of our circuit with 2 bulbs. And we can see from this data a couple of key things. Okay, so ammeter 1 is this one here. We can see that with a reading of ammeter 1 of 0.5, so if this is telling us there's 0.5 amps flowing through this circuit, we can see that how that current is split. And we can see that ammeter 2 is receiving, or bulb 2 is receiving 0.3 amps, and ammeter 3 is receiving 0.2 amps. Okay, and you can see how that changes as we reduce the current. So we know, first of all, that the total current through the whole circuit is the sum of the currents in the different branches. Okay. Now, what we also know is that the potential difference here is the same, okay, across these components. So if my potential difference here is 1.5 volts, I know that my potential difference here is 1.5 volts and here as well, okay, because potential difference in a parallel circuit is the same across each component, okay. Now what we can see is we can calculate the resistance here across these different components. So let's take this bulb A2, okay, let's call this bulb B2. Well, actually, let's call this, yeah, B2. We'll call it B2 because it corresponds to A2 as well. Okay, so let's work out what the resistance across B2 is going to be. Okay, so we know, so remember our equation V equals IR. We know that what the current is, and we know what the resistance. Sorry, we know what the current is, and we know what the voltage is. So we want to work out the resistance. Okay, so resistance is going to equal my voltage, which I know is 1.5, over my current, which I know, and let's take a setting, or let's choose the top row just for this. It will be the same regardless, but let's choose our top row. Okay, so it's going to be 0.3. Okay, 0.3. So that gives me a reading, a resistance reading here of 5 ohms. Okay, now let's do it for the second bulb as well. Okay, so this time we've got a resistance reading again of 1.5 volts, and the current this time is 0.2. Okay, so this time my resistance is going to be 7.5. So my resistor there is 7.5 ohms. Okay, now let's look at the resistance in the whole circuit. Okay, so what is the resistance across the variable resistor, for example? Okay, so let's do a different same calculation but using slightly different numbers. So we've got R here equals still 1.5 volts. This time we've got 0.5 as our current. Okay, and our resistance therefore is 3 ohms. So we can see just by doing some calculations that the resistance, the total resistance in a parallel circuit, is actually smaller than the resistance of these different components. Oh, sorry. And that is an important difference between series and parallel circuits. Okay, so let's look at that rule, what that means. So the resistance, the total resistance, and I'd like you to write this rule down as well. Okay, so the total resistance of two or more components in parallel is less than the resistance of the resistor with the least resistance. Okay, so what does that mean? I'll go back here. So my resistor with the least resistance was this one, 5 ohms. The total resistance was less than that number. It was 3 ohms. Now why does that happen? It's because the current here now has two ways to go. Okay, so the current is that even though the potential difference is the same, okay, the total current entering the combination is going to be higher. Okay, so this part here is quite wordy, so I'm not going to go through it now. I'd like you to read through it and see if you can make sense of this. Okay, so here's an example here that we can work through as well. Okay, here I've got resistance values. Okay, now if I suggest, for example, that my current going and my total current, okay, is 3 amps, okay, and I've got 1 amp going here, 1 amp going here, and 1 amp going here. Oh, actually, let's change that, sorry. I need to do that slightly differently. I could work out what the current is. Let's work out actually what the current is going to be, okay, on this example together. So I'd like you to work through this with me, okay, at the same time. So you're writing down some information here. Okay, we're going to work out I1. So we're going to use our equation V equals IR. We're going to work out I1 as being V1 over R1. In this case, V1 is obviously going to be 6 because we know that the potential difference is the same. R1 is 1. So so the current is 6 amps here. Let's just cross that out as well. I2, okay, so what is the current across the second resistor? So here it is again 6 volts, but we've got 2 ohms of resistance. So we've got 3 amps of current. And I3 is 6 divided by 6. So we've got 1 amp. So you can see that as resistance increases, current decreases, okay, from 6 to 3 to 1. Now what's the total current from the battery? Therefore, it's just we need to add up 6 plus 3 plus 1. Okay, so we add up these currents, and that gives us a total of 10 amps current. So that's how we would work that out. So I'd like you to just pause the video, go through that, draw it out and work it through. Okay, just to finish, okay, we're going to look at a slightly different example, okay, just to finish. So calculating total resistance in parallel circuits, okay. So here I've got 3 examples, okay, three resistors in circuit. Now there is a particular rule that we can use that's to add up or to work out the resistance in this circuit. Recall that for series circuits we just added the resistors together. Okay. Now we do something similar but fundamentally very importantly different to work out total resistance. Okay. So instead of having RT, I have what we call the reciprocal of total resistance, 1 over RT. And what that means is I'm going to have 1 over resistance 1 plus 1 over, or the reciprocal of resistor 2 plus the reciprocal of resistor 3, etc., etc. So in this example, I've got RT, 1 over RT, I must remember to write that, equals 1 over 500 plus 1 over 500 plus 1 over 500, which equals, so 1 over RT equals 6 times 10, not drawing my 6's very well, 6 times 10 to the minus 3. So then if I work that out, I do 1 divided by that, I get an answer of 167 ohms. Okay, so RT equals 167 ohms. Now remember, our rule is that the total resistance in the circuit is less than the lowest one, okay, the lowest resistor, and we can see yes, this is 167. All of our resistors were 500. Okay, so the total resistance is less. Okay. Now, the second part of this question, the last part for today, is that if the current in each branch is 20 milliamps, what is the supply voltage in this circuit? Okay, and all I needed to do for that is just use my V equals IR to say that, well, V equals my current, which is 20 milliamps. Now, not 20, so I'm not going to write it in 20, I'm going to write it as amps. So that gives me 20 times 10 to the minus 3, okay, or 2 times 10 to the minus 4, times 500 because that's my resistance, which gives me a voltage of 10 volts. Okay, so the current, the supply voltage from my battery is 10 volts. Okay, so pause the video, make sure you're clear on that, and show this example of how to work out total resistance in a parallel circuit. Now, finally, your independent task is to complete some exam questions. Okay, so your link for those are on the Padlet, and your teacher may well supply it as well. Good luck, and I will see you for the next lesson.